Alright, welcome to this video about the derivative and its rules for finding the derivative in different scenarios. I anticipate this is going to be somewhat of a long video, so what I'm going to do is down in the description I will timestamp each of the different rules and segments of this video. So if you're looking for a specific rule, you can just jump straight to it. So the first thing I want to talk about, though, is actually notation. So we know we're all talking the same language here. So as far as I know, there's three different ways of writing the notation for derivatives, differential calculus. You have the Lagrange method, the Leibniz, and Newton. And I'm not very familiar with Newton, but after a quick Google search and our friend Khan Academy, I found out about Newton. And not found out about Newton, but found out about how Newton notated his differential calculus. I think you mostly see Newton, the Newton notation in like physics and things like that. I'm not a physics person, so I don't know for sure. All right, so let's talk first about Lagrange method. So if I have a function f and an equation with f, and I'm taking the derivative, then the way I would see that is f. Whoops. Just got to be on the right thing. F prime, like this. There we go. All right, the second derivative would be f double prime. That little mark is of prime. Third derivative, f triple prime. And then fourth derivative and so on. You just use a little number like that. And the same thing as if it was y. You'd just be y prime, y double prime, y triple prime, that kind of thing. If you have it actually written in function notation like this, then it's going to be, f prime of x or f double prime of x. F triple prime of x, and so on and so forth, now using numbers and stuff. Okay, so that's Lagrange method. You see that a lot, especially, like I said, with function notation. Oftentimes it's just an equation is written with a single variable like this. So you see that a lot with, especially in single variable calculus. All right, Leibniz. The derivative of y using notation for the Leibniz notation, the Lagrange notation would simply be y prime. Okay. That would be the Lagrange method, but Leibniz, he did a little bit differently. It's going to be dy over dx. This represents the exact same thing as y prime, dy over dx. Now let me before I get into the second derivative, let me explain how that works. So if I have the equation y and I want to take the derivative of it, I'm just going to use brackets. You can use parentheses, but I kind of like brackets with calculus. I don't know why. It makes me happy. Okay, anyways, so we've got, if I want to take the derivative of this with respect to the variable x, this is what it would look like. This is the operation, take the derivative of y, which gives me dy over dx. And that d is basically kind of like a delta. It's like delta y over delta x. Right? It is the change in y over change in x, the slope, if you will, because that's what the derivative is finding the rate of change. So these are called differentials. Tiny infinitesimal little changes in x and tiny little infinitesimal changes in y is what this notation is kind of meaning. So now, if I wanted to find the second derivative, so let's make some room up here. I'm just going to erase this stuff over here. If I wanted to find the second derivative of y, so here's y. I am first going to take the first derivative, right? And then I want to take the second derivative of that. So I'm going to do it again, right? You'll notice over here, like when I do this, I have this d, the d appear twice. So the way I like to think about it, I don't know if this is actually mathematically correct, but the way I like to think about it is this becomes almost like a d squared. And then you have d squared y, right? Because that appeared twice right there. I have two of those. And I have two of these differentials of x's, dx's right here. So that dx is like its own little entity. So it's not like a d separate, multiplied by an x. It's just the differential of x. So this is going to be dx squared. See how that works? I always thought it was kind of funny that these twos don't line up together, right? This one is up here in between the d and the y, and this one's after the dx. Always kind of weirded me out a little bit until I kind of looked at it like this. And so the second derivative of y using the Leibniz notation is going to look like that. And similarly, if I did this once again, let's do it a different color right here. If I did this again, right, using the third derivative, now I've got three of those d's, right, y, and three differentials of x. So we have that right there. So the third derivative, and then finally, the fourth derivative, and so on and so forth. I just use the numbers. There's your fourth derivative. Okay. Now, Newton had his own little way of doing things. His first derivative is kind of cool. It's just y with a little dot. So like that. That's the first derivative. Y dot is what they call it. Then the second derivative would be y double dot, like so, and y triple dot. Now, I think you could probably do 4 dots for the fourth derivative, but usually Newton just kind of, since he was very much into physics, and as you learn with derivatives, you've got displacement, whose derivative is velocity, whose derivative is acceleration, and then you kind of just stop there. I guess you could go on to the third one, which is called a jerk. So this would be your position, velocity, acceleration, jerk, and then after that, I'm sure there's something, but I don't know what it is. So I guess maybe you could do 4 dots. I don't know. That one's left up in the air because, like I said, I'm not familiar with this notation at all. But there you go. So that's Newton notation. Probably don't see that very much outside of the world of physics and stuff. So hopefully that helps. As we go through this video, I'm going to be switching back and forth between various different notations, Lagrange and Leibniz. I won't deal with the Newton one, but I'll be playing around with these ones here. So it's kind of nice to know that we're all on the same page. All right, to start us off, I just want to talk quickly about derivatives of linear equations, because I feel like to understand what derivatives are, it's really nice to look at something that we're very familiar with, which are linear equations. All right, so a derivative, all a derivative is an equation that represents the slope or the rate of change of another equation. Okay, so for example, I've got this equation right here, y equals x. In fact, I've even got, wait for it, a graph of y equals x right here. There we go. So we've got y equals x. This is what it looks like. And if I'm finding the derivative of this, so let's use our notation that we just talked about. So dy over dx, or you could do y prime. It doesn't really matter. All right. What is the derivative of this? And we haven't talked about any rules yet, but let's just think through this. If the derivative is the slope, or an equation that represents the slope of equation y up here, well, what is the slope of this line? If I look up here, the slope at any point, I can pick any 2 points I want. So let's just pick that point and that point right there, right? I go up 1, so change in y is 1, change in x is also positive 1, so my slope is 1. The derivative of x right here, with respect to x, is 1. Okay, because this equation, y equals x, the slope is 1 everywhere. It doesn't matter where I'm looking at. The slope is 1 no matter where I look. Okay. Similarly, with y equals 2x. No matter where I look at on this graph of y equals 2x, the slope is always 2, right? Linear equations have what's called a constant rate of change. That means the rate of change is constant everywhere, which means if the rate of change is constant everywhere, the derivative is also going to be constant everywhere. So let's do the Lagrange notation this time. So y prime is equal to the derivative of 2x, right? So the slope is 2 everywhere I look. The derivative of 2x is 2. Okay? That is the slope of this equation everywhere. Okay? And finally, we've got this one right here, y equals negative x plus 1. We got a graph right here, and there's negative x plus 1, and you'll notice that the slope everywhere is negative 1. Hey, this plus 1 over here doesn't really do anything. All this does is shift the graph up and down. It doesn't change its slope. So the derivative of this one is negative 1, which makes sense because you have y equals mx plus b, right? That's your slope-intercept form of a line. So your derivative of this, dy over dx, is always just going to be your slope, right? When you're dealing with linear equations, it's just your slope. All right? So I bring that up because as we go through our rules, we're going to be asking ourselves a lot what the derivative of a linear equation is, especially what is the derivative of x. Okay? So derivative of x, this is really 1x plus 0, so the derivative of this with respect to x, and that's an important concept that deal with later, which we won't get into this video, but we are taking the derivative with respect to x and not some other variable. Anyways, the derivative of x with respect to x is 1. Well, I guess let's talk about it really quick. So if I'm taking the derivative of this from both sides, technically what it is dy over dx. And I'm doing the same thing to this side. I am taking the derivative of x like this, right? So what this becomes is dx over dx. And what is something divided by itself? It's just equal to 1. That's why the derivative of x using the Leibniz notation is equal to 1. Okay? So moral of the story here is that when you're dealing with linear equations, the derivative is simply just the slope of that equation, which is what it is for everything. But since linear functions have a constant rate of change, the slope is going to be just a single number. Okay, the next thing I want to talk about, once again, before we get into the individual rules, is the structure of an equation and how the structure, the way an equation is structured, is going to affect how we take the derivative. So over here on the right, I am going to, here's all of our little derivative rules that we're going to be talking about in this video. I'm not going to go into these individually, but what I want to do is kind of see how we would go about taking the derivative of each of these crazy equations. We're not actually going to take the derivative. We're just going to walk through the process of how to use these rules for different situations. Okay? So, for example, this first problem right here, f of x equals 5x squared plus sine of 6x. What I want to ask myself is, overall, what kind of problem is this? What does this look like? So I guess first I should say over here on the derivative rules, we've got operational rules, adding and subtracting or sum difference. The product rule, right? Two things being multiplied together. By the way, this is right here, is I'm taking the derivative of something plus or minus something else. This is taking the derivative of something times something, derivative of something divided by something else. Okay? Down here, the derivative of a constant, derivative of a base where your variable lives raised to a power, kind of things like that, derivative, sine, cosine, whatnot. Anyways, so up here, these ones up here, these three up here are more like operational rules, adding and subtracting, multiplication, and division. And then these ones are equation or function-specific rules. Okay, so as I look at the structure of this equation right here, yeah, I've got an x squared in here. That's going to be a power rule type thing, and I've got a sine function. But overall, like looking at the whole thing, what kind of a rule or what kind of a structure does this have? It's an addition problem. Okay, so the way I would do this, find the derivative of this, is I would refer first to the sum difference rule. Now, let's take a quick look at this one. This one's actually pretty straightforward, which is kind of nice. If I am taking the derivative of two things that are being added together, so I'm going to use the top symbol right here in this plus minus sign, so u plus v, the derivative is simply take the derivative of the first term and add it to the derivative of the second term. Pretty straightforward. Now, you'll be cautionary, or be cautious here, not cautionary, that if you look at the product rule, it's not as straightforward. It's not simply, hey, I'm taking the derivative of u times v, therefore the derivative is u prime times v prime. That isn't, the product rule and quotient rule are much more complicated than this. But for the addition rule, it's just the first one plus the derivative of the second one. So if I were going to take the derivative of this, to take the derivative of a sum problem, what I need to do first is, according to the rule, I need to, right here, the rule, I need to take the derivative of the first term. So what I would do is I would look at this first term right here and ask myself, okay, what kind of structure or rule does this follow? And this is you notice the variable is the base right here, and it's raised to an exponent. This is a power rule. So I'd come down here and look at the power rule, and you'll notice that on all of these rules, like right here, you have u to the n. Okay, I've got this u prime here at the end, right? You see that? The exponential rule, log rule's got it, sine rule's got it, cosine rule's got it, tangent, secant, cosecant, they all have these, hey, take the derivative of whatever the heck u is, right? Even up here in our sum product and sum difference product and quotient rule has them embedded in there. You've got this u prime right there, u prime. I have to take the derivative of that, the u, whatever u is. Okay. Now this part of the rule, especially down here, it has a very special name. We'll talk about it in just a minute. Well, in case I forget, it's called the chain rule. And it's probably the most confusing aspect of taking derivatives until you understand what you're doing, okay? But this is called the chain rule. So let's look at this. So according to the power rule right here, remember, we're not actually going to take the derivative, we're just kind of look through it. The power rule, so if I want to take the derivatives, I look at the power rule. And eventually, along with some other stuff right here, eventually I've got this u prime right here. Eventually I have to take the derivative of my base. So I look in here, my base is x, and I ask myself, hey, what is the derivative of x? And the answer is 1. And now I have finished that rule. I have finished the power rule, which I have now finished the first part of the sum rule. So now the next part of the sum rule says, hey, take the derivative of the second term. So I look over here at the second term right here, and I ask myself, hey, what kind of rule do I need for this part of this this term right here? And it's overall, it's a sine function rule. It's got some other stuff inside of it, but overall it's a sine rule. So I come down here to sine. Sine says, hey, the derivative of sine is this stuff right here. But it's also, not to forget, I have to take the derivative of the inside of the sine rule right there, the argument of sine. I have to take the derivative of it. So after I'm done following this rule, the very end, this chain rule portion of it, says, hey, you need to take the derivative of 6x. And I ask myself, hey, what rule does that solve? Or do I just know what the derivative of this is? Technically, it's a power rule. But as we've talked about before, we know what the derivative of 6x is. That's a linear function. The derivative of 6x is simply just 6. And then we're done. We now have finished the sine rule, which finishes up this part of the sum rule, which finishes up the entire sum rule. Okay? And that's kind of the process you go through as you walk through these derivatives. Let's try another one. It's kind of weird at first, but once you get the hang of it, I have found that this is kind of helpful to look at the structure of things. So let me erase my little markings that I have over here. Okay, let's talk about the next one then. So this time, if we were taking the derivative of this, I want to look at, hey, what is it overall? What kind of a problem is this? So looking at the whole thing, yes, there is an exponential rule in there. There's a log rule in there. But overall, this is a multiplication rule. This is a product rule. Okay. Now, so I would look at the product rule where I have something times something. Okay. Inside this product rule, it eventually will tell me that I need to take the derivative of, actually, let's do that in a different color. I eventually have to take the derivative of the first item, the first term, which is e to the x right here. So I would look at this guy right here, and I'd say, okay, how do I take the derivative of this? Which rule does this follow? This is an exponential rule right here. And part of the exponential rule, like it's got a whole bunch of stuff in it, eventually will tell me that I need to take the derivative of the exponent. So I look at the x and I ask myself, okay, what's the derivative of x? And the answer is 1. Derivative of x is 1, which finishes up the exponential rule, which finishes up, which finishes that part of the exponential rule, finishes the exponential rule, which finishes this part of the product rule. Okay. Now there's other things to the product rule. You see how we got a v here and a u here. But eventually, once again, the product rule will ask me to take the derivative of the second thing that's being multiplied, right? Amongst other things, right? But it's going to ask me to take the derivative of this part right here. And as I look at the structure of that part right there, I ask myself, okay, which rule applies here? This is a logarithm. This is a log base e, the natural log. It's still a log rule right here. So I'm going to follow the log rule, and as part of the log rule, there's a whole bunch of other stuff that we're not going to worry about right now, but as part of the log rule, it says, hey, eventually you have to take the derivative of the argument, eventually, right? So I look in here, there's my argument, and sure enough, I have to find the derivative of this. Technically, it is a power rule, so I would look at the power rule, but we already know what the derivative of 4x is. The derivative of 4x is simply just 4. So that finishes up that part of the log rule, which finishes up the whole log rule, which finishes up that part of the product rule, which, after we do all the other stuff as well, finishes up the product rule, and we're done. Okay, let's try one more, a little bit more scary and complex. Let's erase our little notations we have over here. All right. So h of x, if I'm finding the derivative of this, what rule do I look at as for the whole global part of this problem? This is in general, what kind of a problem is this? I've got sine rules, I've got cosine rule, I got all sorts of stuff. And if you get kind of caught up in that, it does look really scary, but just break it down piece by piece. Overall, this is a subtraction problem. I have a division problem minus a multiplication problem, but it's a subtraction problem. So I come up here to the sum difference rule. The sum difference rule says, hey, when I'm subtracting two things, I eventually, actually right away in the sum difference rule, have to take the derivative of the first term. Okay? So I'm going to look at the first term here in h of x. And I ask myself, what rule applies here? This is a quotient problem. Now it's a division problem. So I'm going to look over here at the quotient rule. Now inside this mess that we call the quotient rule, you'll notice that whatever the numerator is, I eventually will have to take its derivative. Okay, so let's look at just the numerator right there. Okay, so I look at the numerator and ask myself, which rule is this? And it sure looks to me like a sine rule. So I come over here to the sine rule, and the sine rule says eventually you will need to take the derivative of the argument, along with other stuff, but you've got to take the derivative of the argument. So let's look at the argument. 5x squared. Okay, what rule does that belong to? That is a power rule. The base is where the variable lives. So this is a power rule problem. And amongst other things, you'll notice that eventually I have to take the derivative of the base, which in this case, so you can see that that's the base right there, which in this case is just the x. It's not the 5. It's only the x that is being squared. And I ask myself, what is the derivative of x, or which rule does it follow? And hey, I know what the derivative of x is. It's 1. That finishes up this part of the power rule, which finishes the power rule, which finishes the sine rule, which finishes this part of the quotient rule, finding the derivative of the numerator. Now, amongst other things, I also have to find the derivative of the denominator eventually, right? So I would look at the denominator down here and I ask myself, hey, what kind of rule applies right here? I have two functions being added together. So this is an addition rule. So part of the addition rule, coming back up here, is I have to take the derivative of the first term of the addition rule. So I would look at right here and ask myself, okay, what rule is this? And it's an exponential rule. You see how this kind of gets kind of complex kind of quick? But if you just follow the rules and just keep following them. I'm running out of colors is my problem. Let's see, we've done pink, purple, orange. I guess we could do gray. Right in here, so this is an exponential rule, and the exponential rule, right here, says eventually, right, we have to take the derivative of the base. Oh, sorry, I'm circling the wrong one. That is the power rule. My bad. Here's the exponential rule right here. Eventually, we have to take the derivative of the exponent. That's how I knew it was the exponential rule, is because the variable lives up here in the exponent. So I look at this little guy right here and I say, hey, what rule is that? And it is a power rule. So I look up here at the power rule, and the power rule says eventually I have to take the derivative of the base. And I say, okay, well, what is the derivative of my base here? Oh, the derivative is 1. The derivative of x is 1. So that finishes up that part of the power rule, which finishes up that part of the exponential rule, which finishes up the first half of the sum difference rule. Now I have to finish the second part. This one's going to be a little bit quicker. The second part says eventually I have to take the derivative of the second term. All right, well, that one's not too bad. What is the derivative of x? We already know what that is. That's 1. Okay, so that finishes up that part of the sum difference rule, which finishes up the whole sum difference rule, which finishes up finding the derivative of the denominator for the quotient rule, which finishes the first part of the subtraction rule, right? The whole thing was the subtraction rule. The whole idea here was finding the derivative of the first term, so that finishes that up. Now, we have to find the derivative of the second part of this subtraction rule. That's this guy right here. I look at this, and it is a product rule. So I jump down to the product rule, which says, hey, eventually we need to take the derivative of the first part. And so I say, okay, what's the derivative of cosine? Okay, cosine eventually, so here's, whoops, that's not what I wanted to circle. Cosine will eventually say, hey, you need to take the derivative of the argument, right? The cosine rule tells me that. And that's this part right here. So I find the derivative of that, which is the power rule. Oh, I haven't used pink over here yet. So this is the power rule. So I come over here to the power rule, and the power rule eventually says, hey, you need to take the derivative of the base. So I look at the base, and the base is just x, and the derivative of x is 1, which finishes up the power rule, which finishes up the cosine rule, which finishes up the first part of the product rule. But then the product rule says we have to take the derivative of the second part. That would be this right here. Hey, that's another exponential rule. We already know that eventually part of the exponential rule says that I have to take the derivative of the exponent, and the derivative of the exponent, 2x, is 2, which finishes up that part of the exponential rule, which finishes up the exponential rule, which finishes up this part of the product rule, which completes all of that product rule, which now completes the second part of the the difference rule, which completes the derivative. Now, that was a mess, but hopefully from that little explanation, we didn't even find the derivative, right? We just kind of walked through it, but hopefully that mess of explanation kind of helps you see how each of these are linked together, or I should say chained together, as this is what the chain rule is. It's taking, it's chaining them from one function to the next when you have functions inside of functions inside of functions. So that is a kind of an explanation for the structure of these, of how to take a derivative, and also kind of an explanation of probably the most complicated rule about taking derivatives, or the one that gives people the most heartache, is what's called the chain rule. But it's not that bad. You just follow the rules, and you know when you're done when you stop following the rules. I know my students always ask, how do I know when I'm done? I say, well, you're done when you're done. So you notice on each of those chains, I finished when I knew what the derivative was. Like on this one, right, I'm just cell right here. When I got down to this and I had to ask myself, hey, what's the derivative of 4x? I didn't need to use another rule. I know what the derivative of 4x. It's 4. That ended that chain because I knew what the derivative was. Okay, so that's kind of an explanation about structure. All right, let's talk about the sum difference rule. We've already kind of hit on it a little bit. This one's pretty straightforward. If I'm finding the derivative of two things being added together or two things being subtracted from each other, the sum difference rule says I can just take the derivative of each of them separately. So I can find the derivative of the first term, add it to the derivative of the second term if I'm doing addition, and minus them if I'm doing subtraction. It's really straightforward. So let's look at this one. I'm going to use some very basic equations, since thus far we have only talked about linear equations. So if I am finding the derivative of this is overall, this is a sum rule. This is an addition rule. So I find the derivative, f prime of x. The derivative of 5x, or what is the slope of this equation everywhere? It is 5. And this, so then plus, so I've taken the derivative of the first part. Now I need to take the derivative of the second term, which is 2x. So the derivative of 2x is 2. And my answer is 5 plus 2. Or, if you want to, you can say it's 7. Which makes sense because if I add these two together, before I even do any calculus, I get 7x. And what is the derivative of 7x? It is 7. Okay, this rule down here, same exact thing, just looks more complicated. We've got a whole bunch of terms. They're separated by plus or minus signs, which it doesn't matter. The sum difference rule basically says I can take the derivative of each of these separately. So y, I'm going to use Leibniz notation, dy over dx is equal to, I need to find the derivative of this one. Derivative of negative 2x is negative 2. The derivative of 8x is positive 8. The derivative of negative 4x is negative 4. The derivative of 5x is positive 5. And the derivative of 6, ooh, it's not 6, be careful. What does this look like on a graph? If I have y equals 6, that is at 6, it's a horizontal line at 6, right? So what is the slope of this everywhere? It's just 0. The slope is 0. That's actually part of the constant rule right there. The constant rule, if you take the derivative of a constant, you just get 0. So there is my derivative. Now if I clean that up a little bit, I get, let's see, negative 2 plus 8 is 6, minus 4 is 2, plus 5, oh, is also equal to 7. How about that? I did not mean for that to happen. That's okay. So the derivative of this is also equal to 7. Now, once again, before I did it in calculus, if I can combine some terms together to make my life easier, that's all the better, right? Negative 2x plus 8x is 6x, minus 4x is 2x, plus 5x is 7x plus 6. So we have the equation that we really started out with was 7x plus 6. It's still a linear equation. All right, this plus 6 just moves the graph up and down. It has nothing to do with the slope. The slope of this graph is 7, so the derivative is 7. Slope is 7 everywhere. That's the sum difference rule, so pretty straightforward. We're going to hold off on the product and quotient rule. Those are much more complicated. They're not as straightforward. One of the things I see a lot of people do is they assume the product and quotient rules work the same as the sum difference rule, where you could just simply find the derivative of the first thing and times it by the derivative of the second thing. And that is not correct. You will not get the right answer if you do that. All right, let's talk about everybody's favorite rule, the power rule. So the power rule, if we look over here, the important thing to note on the power rule is that u is a function of x, okay? So u, the base, is where your variable lives. The variable does not live in the exponent. If it did, it would be the exponential rule. People get these two rules messed up all the time. So it depends on where your variable lives. Okay, you'll notice on this one right here, my variable is the base of this expression right here. Okay, so the power rule is pretty straightforward. What you do is you basically just take the exponent, whatever it happens to be, bring it down out in front, and leave the base just the way it is. You can see that right here. So I bring the n down in front, times it by, leave the base just the way it is, subtract 1 from the exponent, and then our favorite little rule, the chain rule, times it by the derivative of whatever the base happens to be. Okay, so over here we've got dy over dx. Okay, so the power rule says, okay, so first I want to identify my base, just so we know. So this is my base right here. Okay, so I bring the 3 down. I leave the base just the way it is, which in this case is just x. I subtract 1 from the exponent, so that becomes a 2. And then technically I times by the derivative of the base. Well, what is the derivative of our base, which is x? Derivative of x is 1. So that is our answer. The derivative of x cubed, because I would just be timesing by 1, right, which doesn't do anything. The derivative of x cubed is 3x squared. So look at this example right here. Overall, this is a sum difference rule, but the sum difference rule says I can take the derivative of each of these separately. So we've got f of x, so the derivative of that is f prime of x. The derivative of this first term, x, is just 1. The derivative of x to the 4th, this is a power rule, so I bring the 4 down. I leave the base just the way it is. I lower the exponent by 1. And I technically times it by the derivative of the base, which is also 1. So 4x cubed times 1 is just 4x cubed. And then I take the derivative of this last term. Well, it's a constant term. It's just 8. So the derivative of a constant is 0. So this is the derivative of that. Now I want to throw one more in there while I'm thinking about it. Let's come up here. What if I had something like this? Y equals, let's do 2x to the 5th power. Okay, and I want to find the derivative of that. Once again, this is a power rule problem. I want to identify the base though. So we used green over here to identify, well, yeah, green to identify the base. So this is my base right here, 2x. The reason why it's 2x and not just x is because it's in parentheses. All right, so when I take the derivative of this and I follow the power rule just the way it is, I bring the 5 down. Well, let's see, let's first do the dy over dx, right? Bring the 5 out in front. I leave the base just the way it is. and then I lower the exponent by 1, so that's 4. But then I have to remember, the part of the power rule says, hey, you need to times it by the derivative of your base. So I still need to multiply by the derivative of 2x. Well, 2x, that's a linear function. The derivative of 2x is just 2. And then I'm done, because I times it by the derivative of the base, and I knew what that was. So this is the derivative of that. Now you can clean it up. You can do 2 times 5 and get yourself 10 or whatever. But that's the derivative of that. So that's the power rule. Pretty straightforward. But if you have something else inside the base other than x, you got to remember that chain rule. Okay, I want to take a quick little detour. Hold on, let me move this. All right, that's better. I want to talk about a special case of the constant rule. Like over here I have a constant rule. It's just, hey, if it's a constant, it's 0. But what if I have something like this, like a constant in front of, say, a power rule problem? Now, at first glance, I might think to myself, gosh, this is a product rule, because technically it is, right? Technically it's a product rule problem. So what I want to do is I want to find the derivative of this. I am going to use the product rule, even though we haven't talked about it, but this is basic enough. I think it's going to be okay. Let me just move this guy down a little bit. There we go. Okay. So if I'm finding the derivative of this, I'm going to treat this as 5 times x squared. So this is a product rule problem. But I want to show you what we do if the problem we're dealing with would be a product rule, but if one of the terms is a constant. That's kind of what I'm looking at right here. They're not both functions, just one is a constant. So derivative of y, let's call it dy over dx. Okay. All right, according to the product rules, I look through this. The first thing I want to do is take the derivative of my first term. Okay, so that would be the 5 right here. The derivative of 5, it's a constant, is 0. Okay, then according to the product rule, the next thing I do is I times it by the derivative of, or not the derivative, just v, just the second thing I'm multiplying by. So I'm going to times it by x squared. All right. Then the next thing, I have an addition sign, and then it wants me to find the derivative of the second term that I'm multiplying by, or the second expression I'm multiplying by. We know that the derivative of x squared, that's a power rule problem, is I can bring the 2 out in front. That becomes 2x. The exponent becomes 1, right? Technically it's 2x to the first power. And then the other part of the product rule is multiply it by u. So that's 5. Now, as I clean this up, right, you'll notice that because this is 0, these two terms just go away. It's going to be 0 plus 10x. Now, watch what happens if I went back up here and just did the power rule and just like left the 5 right there. Just didn't even worry about it. I would have dy over dx. I would bring the 2 down and I would multiply it by what is out in front. So that becomes 10. Leave the base just the way it is. Lower the exponent by 1, and then technically times by the exponent, the derivative of the x, which is also 1, and I get 10x, right? So what's nice, if you are multiplying by a constant, you don't have to do the product rule. All it is find the derivative of this part and times it by your constant. For example, down here, if I'm finding the derivative of f of u, this is going to be f prime of u, okay? According to the product rule, I've got a constant right here, so the derivative of that constant is 0 times u plus u prime times that constant. And what I'm left with, so that always will go away because this is a constant. That's always going to be 0. That part's always going to go away. And I'm always left with whatever my constant is, or I'm going to use c for constant, times the derivative of the second part. That's what I'm left with. It's a special case of the product rule and makes life really nice when you're dealing with constants in front of expressions. So it's simply take the derivative of the expression and multiply it by the constant. All right, this is a good time to talk about additional sneaky power rules. So if you look at this equation right here, at first glance you would think, oh, this has the structure of a quotient rule. And you could solve this using the quotient rule, but you'll notice the quotient rule is a mess. So we would prefer not to do that if we can. So what we can do, though, is we can be a little bit proactive, and before we do any calculus whatsoever, we can make this more calculus friendly. For example, I've got this x cubed on the bottom, or in the denominator. Now, The power rule. It does not say that, if you notice the notation here, this power rule does not exist in the denominator of something. It's got to be in the numerator in order to do the power rule. Okay, you can't just apply this wherever the thing happens to be, wherever the expression happens to be in a problem. It's got to be on ground level in the numerator. So the question is, can we do something to this that will bring it up to and place it in the numerator? And the answer is yes. Without doing any calculus yet, we can rewrite this equation as, I'm going to leave the 4 down there though, 5/4 times x to the negative 3 power. Or you could write it as 5x to the negative 3 over 4. I like putting it outside out here because it just helps me prepare myself for the power rule already. So these two expressions are, actually all 3 of these expressions, are the exact same thing. It's just if I leave it like this, I'm going to have to do the quotient rule, which is a mess. But you can do it. It's not a problem. It's just a mess. But if I write it like this, then I have prepped myself to do a much easier rule and do the power rule. So as I take the derivative of this, I got dy over dx. My base is x. The exponent is negative 3, and that's fine. There's nothing in here that says the exponent has to be a whole number or a positive number. In fact, in a minute we'll find out it can be a fraction, and that's fine too. So I'm going to bring the negative 3 down, and I'm going to multiply it by whatever's already out here. We just talked about that with the constant rule. So negative 3 times 5/4 is negative 15 over 4. Leave the base just the way it is, and remember to subtract 1 from the exponent. So that's a negative 4. And then technically times by the derivative of the base, but the derivative of x is 1, so we're timesing by 1, and that would be our answer right there. That is the derivative of this expression. You'd get the same thing if you did the quotient rule. It's just a lot more work. Okay. So right here we've got a radical, and you'll notice over on my list of derivative rules, I don't have a radical rule. But that's because with a little bit of being proactive, we can make this into a power rule. If you remember, your radicals can be written as rational exponents. So I'm going to leave the negative 7 alone, and my base is x. Okay. When I have a radical like this, the index value right here becomes the denominator of the rational exponent. So this is really x to the 8/5 power. This fifth root of x to the 8th and x to the 8/5 power are the exact same thing. And now that I've written this, notice I haven't done any calculus yet, just rewriting some stuff. You'll notice that now it is ready to do the power rule. So I can take the derivative of f prime of x, and I get negative 7 times 8/5 is negative 56/5 x. And then I need to subtract 1 from this. So 8/5 minus 1, that's 8/5 minus 5/5, right? That's going to be 3/5. And then technically times the derivative of x, which is 1. So there is my answer to this one. So if you're a little bit proactive, you can do simpler rules. In fact, this one you'd have to do it, but sorry for that really loud noise. But that would be my answer to that problem right there. Okay, let's talk about the exponential rule. So the exponential rule, people get exponential and power rule mixed up a lot because you think, oh, it's got an exponent, therefore it's the exponential rule. But it all depends on where the variable lives. So going back to the power rule, you'll recall that the variable lives in the base, right? So it'd be x to some power, or something like that. Whereas the exponential rule, your variable lives in the exponent spot. This is where the variable lives, is up here. All right. So y equals 2x. So first off, the derivative of y is dy over dx. And then following the rule you'll notice says, hey, just write down the expression exactly the way it looks. Like those match, right? A to the u, a to the u. So write it down exactly how it looks. So 2x times the natural log of the base. It's always the natural log. So times the natural log of our base. So the base is a. In this case, our base is 2. So natural log of 2. And then we always have our little chain rule friend right there. Times the derivative of the exponent in this case. So the derivative of x is just 1. And that would be our answer right there. We could simplify by getting rid of the times 1, but after that, there's nothing else we can do. We can't multiply the 2's together, right? This 2 is inside of the log function. So 2x times the natural log of 2 would be the derivative of y equals 2x. All right, let's take a look at the next one. This is a special case of the exponential rule, and we'll see why in just a second. So first off, we got the derivative of y, which is dy over dx, equals e to the x. Now remember, e is just a very, very special number, okay? Kind of like how pi is actually a number, right? But it's not a variable. And e, called Euler's number, is 2.718 something, 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 okay? But it's about 2.7. It's a very, very special number, used in finance a lot. And in calculus. We like it in calculus, and we'll see why in just a second. So following the rule, e to the x, I'm just going to copy it down, so e to the x, right, times the natural log of the base, which in this case our base is e, the natural log of e, times our derivative of the exponent, which is x, so which is 1. Okay. Now this we can clean up a little bit further, especially times 1 can't really do anything with that. I mean, that just goes away. But natural log of e. So if we've forgotten how logs work, so we got natural log of e is equal to what? Okay. Well, natural log, all that means is log base e, is what natural log means. So we're taking log base e of e is equal to what number? So this is asking us, hey, what is the exponent of e? What is e's exponent that gets us an answer of e? Well, e to what power equals e? It's got to be equal to 1. So natural log of e is just equal to 1 as well. So the derivative of e to the x is just e to the x. It's itself, which is so cool. And that's one thing that makes, that's one reason why e is such a special number, is that it is its own, or e to the x is its own derivative. All other exponential ones will not work out that way. You always have this natural log of something. Okay, but the natural log of e goes away with e to the x. So the derivative of e to the x is e to the x. So look at this last one right here. So we got f of x, so we're going to say f prime of x, right? This is that e again, our base. That's wonderful. We love it when our base is e. So the first thing we're going to do is copy it down, e x to the 5th. Now because my base is e, this part right here, I can just skip that part because my base is e. I know it's going to be times by 1, which is fine. And then I just have to remember to multiply by the derivative of the exponent. So I look up here at the exponent. This is a power rule problem because, I should say, look at this exponent, because the variable is in the base, right? So the derivative of x to the 5th using the power rule is 5x to the 4th times the derivative of x, which is 1. And there is our answer right there. Ex to the 5th times 5x to the 4th is the derivative of f of x. And that is the exponential rule. All right, now let's take a look at the log rule. All right, so the log rule is right here. This is when you have are finding the derivative of a logarithm. We can have our base be anything, and we'll see what happens, what's special when we do log base e, the natural log. So let's do this one first. So we got f of x, so that's going to be f prime of x. And then log, by the way, it's always really good to write these down. Don't just take the derivative of the side and don't write anything else with it. Especially in calculus, sometimes we're dealing with 2, 3, 4 functions at a time. You know, 2 functions and their derivatives and stuff. And so it's really important to keep them separate because they are 2 different things. So we want to make sure we label them correctly. All right, so log base 3 of 5x. So according to the log rule, when I'm taking the derivative, it's simply 1 over the argument. That's the part inside of the log function. So in our case, that's 5x. So it's 1 over 5x times 1 over the natural log of our base, and it's always natural log. Base is 3. And then finally, once again, we've got our good friend, the chain rule. We have to multiply by the derivative of the argument. So that's the 5x right here. So we're going to times by the derivative of 5x. We know what the derivative of that is. Since it's just our little linear friend, it's 5. Now make sure that we are timesing it by 5, not 1 over 5. That 5 is in the numerator up here. Okay. Now as we clean this up a little bit, we got 5 times 1 is 5. And on the bottom we have 5x times the natural log of 3. We can't combine anything on the bottom because that 3 is part of the argument of the natural log, so we can't multiply it by anything. But notice our 5's do cancel out. So really the answer to this one is 1 over x natural log of 3. So that's the answer to that one. Okay, now let's take a look at the special case right here. Now remember, natural log is the same thing as log base e. Okay, so they mean the exact same thing. So let's come back over here. So we're taking the derivative. So this one is going to be dy over dx equals 1 over the argument, which in this case is just x. So 1 over x times 1 over the natural log of our base, which is base e. So natural log of e times the derivative of the argument. Well, the derivative of x with respect to x is 1. As we clean this up, timesing by 1 doesn't do anything. Natural log of e is also equal to 1. So we have 1 divided by 1 is 1. So we have our final answer here is 1 over x. So the derivative of the natural log of x is 1 over x. Or it's also kind of nice, I would normally leave it like this, but also recognize that is x to the negative 1 power. Okay, they mean the exact same thing. It's nice to recognize that the derivative of natural log of x is x to the negative 1 power. Okay, that's a good one to memorize too. Natural log of x's derivative is 1 over x. You see that? We see that a lot. Okay, next one, g of x. We've got g prime of x is equal to the natural log of 3x squared plus 6. So overall, this is a sum difference rule. So we can take the derivative of each of these separately. So the derivative of natural log of 3x squared, it's 1 over 3x squared times the natural log of the base, but it's natural log already. So the base is e, so that's just going to be equal to 1. So once again, on this, if I have base e, I don't have to worry about that part. I do have to worry about the chain rule, though. Always got to worry about the chain rule. Times the derivative of the inside. So I look at the inside here. This is a power rule problem. So I bring the 2 down. That becomes 6. So it is 6x, technically, times the derivative of x, which is 1. And there is the derivative of the natural log of 3x squared. That's the first part of the sum difference rule. The second part, take the derivative of the other term. This is a constant. So the derivative of 6 is just 0. So it's plus 0. So our final answer here is we've got 6x over 3x squared, which 6 over 3 simplifies to be 2. This x cancels out one of the x's on the bottom, and our answer is 2 over x. And that is the general log rule intermixed with the special case when the log is base e, or natural log. All right, sine and cosine. So these two trig functions, we'll see that they have the rules down here. Sines is pretty straightforward. It is simply just the cosine of the argument, which is actually kind of fascinating. If you ever get a chance, take a look at what these graphs look like. Remember, the derivative is just the slope of that graph. So sine's derivative is the slope of sine, and it actually does match up with cosine, which is pretty cool. So if you get a chance, take a look at that and kind of explore all that idea. So derivative of sine is cosine. Then we don't forget the chain rule. So up here we got dy over dx is equal to the derivative of sine is cosine. Leave the argument just the way it is, and then times by the derivative of the argument, which in this case is 1. So the derivative of y equals sine of x is cosine of x. All right, let's take a look at cosine. Similar, but you got to be careful because derivative of cosine is not sine, it's negative sine. So don't forget the negative symbol there. So here we go. F prime of x is equal to, cosine, this is cosine rule, so I look at cosine here. The derivative of that is negative sine. Leave the argument of the cosine function just the way it is. Don't change it at all. Okay? And then times it by the derivative of the argument, that chain rule. So derivative of pi x. Remember, pi is just a number. So this is a linear function right here with a slope of pi everywhere. So the answer to this one, the derivative of cosine of pi x, is negative pi sine of pi x. That's the derivative. Okay, the third and final one right here. This sine to the fourth power of 2x, that is the same thing. So I'm not going to do any calculus just yet. I'm just going to rewrite this so it's a little bit more calculus friendly. This is the exact same thing as saying sine of 2x, right, raised to the fourth power. Okay, it's the whole thing raised to the fourth power. Sine of 2x times itself 4 times, a total of 4 times. So now we're ready to take the derivative. And as I look at this, this is not this is not a sine rule problem. This is a power rule problem. You know, so I've got an exponent right here. My variable lives inside the base. Yeah, it's inside of a sine function, but it is inside this base right here. This is first and foremost a power rule problem. So I've got f prime of x is equal to, I'm going to bring the 4 down, that's what power rule says, right? Leave the base just the way it is. Don't touch it. Just leave it that way. And lower the 4 by 1, so that becomes 3. Okay, so that was the power rule, but then I have to honor the chain rule, which says, hey, take the derivative of the base. So I need to look at right here, sine of 2x. The derivative of sine of 2x is going to be cosine, leave the 2x just the way it is, right? And then I have to take the derivative of the argument of that, which is the derivative of 2x, which is 2. In fact, I'm going to do that just for fun in a different color. That part right there. Okay, so this was a function within a function within a function. So we had to apply the chain rule twice here. Okay, and you could clean this up. You could call it 8 sine cubed. In fact, I'll do that. I'll kind of clean it up a little bit. F prime of x equals 8 sine cubed of 2x times cosine of 2x. And there is our derivative. Those are the sine and cosine rules. All right, next let's take a look at tangent and cotangent. So tangent and cotangent, so I'm actually looking at this one right here and this one down here. The reason why I put those ones together is you'll see their pattern for their derivative is very similar. Tangent's derivative is secant squared. Cotangent's derivative is negative cosecant squared. So they're kind of related. In just a second, we're going to look at secant and cosecant, and you'll see that they are also formatted very similarly. All right, so tangent. I have finding the derivative of tangent, so this is dy over dx. Derivative of tangent is secant squared. Leave the argument just the way it is. So secant squared and leave the 5x just the way it is. And then we get our friend the chain rule, which says, hey, don't forget to take the derivative of the argument. So here we got the argument is 5x. The derivative of that, I know what the derivative of that is without even looking at a rule. I know the derivative of that is 5. And we're done. So the derivative of this is 5 times secant squared of 5 of x. Okay, let's look at the next one. We've got cotangent of x squared. So f prime of x is equal to cotangent's derivative. So cotangent's derivative is negative cosecant squared. Leave the argument just the way it is. Okay, x squared. And then we got our friend the chain rule, and then times by the derivative of the argument. So the derivative of the argument, this is a power rule, but I know this one just off the top of my head. The derivative of this is just going to be 2x is the derivative of x squared. So there is our derivative for that problem for cotangent. And if you wanted to, you can move the 2x out in front, so it would be negative 2x cosecant squared. Nothing wrong with leaving it here at the back end too. All right, let's try this one, y right here. So we got dy over dx is equal to, so I've got a constant out in front. If we remember our constant rule from a while back, we can just, you can kind of just ignore it and just multiply it back in at the end. I'm just going to kind of leave it there and kind of treat it as part of the cotangent. So my derivative of negative pi cotangent is going to be, well, let's see, it's going to be negative pi times the derivative of cotangent, which is negative cosecant. So I am going to get the cosecant squared in there, but it is negative, which is going to change this to a positive pi cosecant squared. Leave the argument just the way it is, like so. And then don't forget to multiply by the derivative of the argument, which once again is 2x. So the derivative of that is 2. So our final answer is, if you want to move the 2 out front, it's positive 2 pi cosecant squared of 2x. So because the cotangent started out as negative, its derivative is negative, so that means it's going to end up being positive. All right, here is secant and cosecant. So we're looking at these two down here. Okay, and you'll see that they are formatted very similarly. The derivative of secant is secant times tangent, and then obviously the chain rule. The derivative of cosecant is kind of the same format, but this time it's cosecant and cotangent, but it is negative. So really quick, over all these trig functions, you got 6 trig functions right here. You'll notice that 3 of them result in a negative derivative and 3 of them result in a positive derivative. If you notice the pattern here, so negative for cosine, which starts with a C. Cosecant is also negative. Notice it also starts with a C. And cotangent is negative, also starts with a C. So one way to remember is all the C's, the 3 trig functions that start with C's, have negative derivatives. So I don't know if that's helpful or not, but it's kind of nice to see that little pattern right there. All right, so let's take a look at secant. So we've got the derivative of y with respect to x. So this is dy over dx is equal to secant's derivative. So secant's derivative is secant tangent. So secant, leave the argument just the way it is, 8x squared minus 2x, times tangent, once again, argument again, right? They both have their own, oops, I pointed to the wrong one. They both have their own argument. The arguments stay the same, 8x squared minus 2x, okay? And then we got to remember, that's the end of the secant rule, we got to remember the chain rule, which says times by the derivative of the inside of the argument. Well, inside the argument, this is a sum difference rule, so I can take the derivative of these separately. They're both power rules. So the derivative of 8x squared is 16x, and the derivative of negative 2x is negative 2. Now, be very careful here. What I have written right now is incorrect. There is something wrong with this. And you'll notice it's actually part of the chain rule right here. My chain rule's derivative has 2 terms in it. Okay? Right now, the way it is written, all of this needs to, if you'll notice down here, all of the derivative of secant, all of this is getting multiplied to all of the derivative of the argument. And what I have right now, because it's only the derivative of secant is only getting multiplied to part of the derivative of the argument. It's only getting multiplied to 16x. I need it multiplied to both of these. It's an easy fix, but it's one that we forget quite often, so I need to make sure I put this in parentheses. And now that is the correct derivative. That way, the entire derivative of secant is getting multiplied by the chain rule. So you have to remember to do that whenever your derivative has more than one term in it. All right, next one, cosecant. So let's take a look at this one. So we got f prime of x. Derivative cosecant of e to the 2x. So overall, this is a cosecant rule. There is an exponential rule inside of there, and technically a power rule inside of that. But let's just worry about one at a time. So the cosecant rule says the derivative is going to be negative cosecant of our argument, e to the 2x, cotangent of our argument, e to the 2x, and then times by the derivative of the argument. So derivative of e to the 2x. We just did this one earlier. The exponential rule. So it is base e, so we don't have to worry about this part right here because the natural log of the base, which is e, natural log of e is 1. So it's really just e to the 2x times, there's another chain rule, the derivative of the exponent there. In fact, let's do this in a different color. I'm doing this guy right here. So times the derivative of 2x, which is 2. So there is our derivative right there. You can clean it up a little bit, maybe move the 2 and the e to the 2x to the front, or you can just leave it like that. That's fine too. But that is the derivative of cosecant. All right, well that takes care of all of our equation rules or function rules that we're going to be worrying about for this video. There are other ones, like you can find the derivative of absolute value functions and things like that, but we're not going to worry about those in this video. But now we get to the brutal ones. We got 2 left, the product rule and the quotient rule. So these can end up being a lot of work. And remember, they're not as straightforward as the sum difference rule, where the sum difference rule just said, hey, if I'm adding 2 things together, I just take the derivative of each of them separately and I'm good to go. Okay, you'll see the product rule and definitely the quotient rule are much more involved. There is other stuff involved in them. All right, so the first one I want to do is this one right here. So we've got y equals 3x to the fourth times x squared. Now, those of you who are savvy enough to look at this say, well, hey, why don't we just multiply those together first? And, 3x to the fourth times x squared, that's what, 3x to the sixth, right? And then take the derivative of that. So that's really what y is equal to, right? So the derivative of that is just 18x to the fifth, right? And you could do it that way, for sure, 100%. But I want to show you that following the product rule here will get us the exact same thing. So we've got this one down here. So we're going to apply this to the product rule. Now you notice that the product rule has two parts to it. You got one item or one function or thing times another one. Okay, so notice the product rule only has two things in it being multiplied together, which if you look down here on G, I've got three things being multiplied. So we'll have to look at that when we get there. Well, here I do have two things. So this is 3x to the fourth. There's one times this other one. Okay, so here we go. Let's take the derivative. So the derivative of y with respect to x is dy over dx. And according to the product rule, here's what we got to do. We are going to take the derivative of the first part. So the derivative of u. So I look at this. The derivative of this is a power rule problem. The derivative of 3x to the fourth is 12x to the third. I like putting this in parentheses, even though it's only got one term in it. I still like doing it because in the end, I want to see two sets of parentheses being multiplied together with a plus sign, two sets of parentheses being multiplied together. I like to see each of these individual things. It helps me stay on track and I don't forget something. Okay, the next part says, hey, put v just the way it is. Don't touch it. Don't take the derivative of it. Just put it in there just the way it is. So times, so once again, I'm going to put this in parentheses, x squared. Okay, plus, this time we're going to take the derivative of v. So I'm going to take the derivative of v. When I look at this is a power rule problem as well. The derivative of x squared is 2x. And we take u just the way it is. So 3x to the fourth. And we are done. We have now taken the derivative. That is the derivative of y with respect to x. Now, if we clean this up a little bit, we get dy over dx equals, what is this, 12x to the fifth. So we get 12x to the fifth plus, what is that, 6x to the fifth, right? Those are like terms, so we can add them together, and we get 18x to the fifth. And you'll notice that's the exact same thing we had up here when we multiplied them together first and then took the derivative. We got the same answer. So we can see that this is the product rule. If I had just taken the derivative of u and times it to the derivative of v, I would have gotten the wrong answer. So the product rule, okay, more to it than just simply taking the derivative of each of them. Okay, so then you might wonder, well, why don't we just multiply them together all the time, right? And just do it like a power rule problem. Well, if you look at this one down here, f of x, we can't do that. Sine times cosine. This is as simplified as this expression gets. We can't simplify it any further. So once again, I've got this item or this expression multiplied by this expression right here. So the derivative of f of x is f prime of x. Okay. Product rule says take the derivative of the first. So we get sine of 2x. Which is, look at the sine rule, sine of 2x, the derivative is cosine of 2x, times the derivative of the inside, right, the chain rule, so times the derivative of 2x, which is 2. I'm going to put it out in front. So 2 cosine of 2x. Okay, that was that first part, and then we have to write down the second part, v, just the way it is. Don't make any changes to it. Cosine of 3x. Okay, plus the derivative of cosine of 3x, so derivative of cosine is negative sine. So we've got negative sine of 3x times the derivative of the argument, which is 3. Well, the argument is 3x, so its derivative is 3. I'm going to just put it out here, so it's going to be a negative 1 times 3 is negative 3. And there's the derivative of v times u, just the way it is, sine of 2x, like so. Okay, and that's it. That is the derivative. Okay, so that's the derivative. Now you can clean it up, do a little bit of arithmetic stuff and manipulation and whatnot to clean it up, but that's the derivative. We're done doing calculus. So we've got 2 cosine of 2x, okay, times cosine of 3x. So unfortunately, we can't combine them together because our arguments are different. But we do get 2. We can call it cosine of 2x, cosine of 3x. And then here we got minus 3. Same thing with these two. I can't combine them together because they have different arguments. I will put the 2x first, though, because why not, right? I did the 2x first over here. And, whoops, I almost wrote just 3x right there. Sine of 3x. And that's cleaned up a little bit, not much, but there you go. That is the derivative of sine of 2x times the cosine of 3x. All right, now on G. This one's a little bit different. I've got 3 expressions being multiplied. Now, with the sum difference rule, it doesn't matter how many expressions you have being added or subtracted or both. You just take the derivative of each of them separately. However, with the product and the quotient rule, it does matter. So the product rule, this rule is for 2 things being multiplied together, which means, at first glance you might think, well, we have 3 things here. So what's the rule for 3 things? Well, there's not one. We just use the rule for 2 things. We just have to be sneaky about it. So, for example, instead of treating this as 3 things being multiplied together, I'm going to treat it as only 2 things being multiplied together. I'm going to group these, either doesn't matter which 2, I'm just going to take these 2 though. I'm going to group these 2 together, and they're being multiplied to sine of x. Now, I have a u. This whole thing right here is u, and this whole thing right here is v, right? U times v. And if you look ahead a little bit, you're going to see how this is going to get complicated pretty quick. So I'm going to come way over here. G prime of x is equal to, here we go, the derivative of u. Now I've defined u to be these 2 combined together right here. I could have just had it be e to the x and had these 2 combined together to be v. It doesn't matter which way you do it. But I've decided that these 2 being multiplied together is what my u value is. So I look at this and ask myself, okay, how do I take the derivative of these 2 things right here being multiplied together? Well, that's a product rule. So I'm inside of another product. I'm already doing the product rule. I'm now doing another product rule with these. So I'm going to treat this as my new u, and I'm going to treat the 2x as my new v. Okay? So over here, I guess we'll just keep the same colors. So over here I need to take the derivative of my new u value. So derivative of e to the x, that's an exponential rule, and that one you should just memorize. The derivative of e to the x is e to the x. Okay? Leave the second one, our v value, just the way it is, right? So that's v. Leave it just the way it is. Okay? Plus the derivative of v, right? So the derivative of v, which is derivative of 2x, is 2. Okay? Times the first one just the way it is. So e to the x. All right? What we just did right there, that was the derivative of u, our first part of the product rule. We just finished the product rule to find that, but that is u prime right there. I'm going to put it in parentheses because it is 2 terms, so I want to make sure I have that in parentheses. So that's u prime. Times v, just the way it is, so sine of x. Plus the derivative of sine of x. So derivative of sine of x, that's cosine. So this is going to be cosine of x times the derivative of x, which is 1. And then times by u, just the way it is. So e to the x times 2x. And that is the derivative of e to the x times 2x times sine of x. It's kind of a mess, but that's the way it just is going to work out. So if you ever have more, I'm not going to even bother trying to clean this up. If you ever have more than 2 terms that are being multiplied together, what you're going to have to do is you're just going to have to group some of them together. So that way you have to end up doing the product rule multiple times in the same problem. Okay. I guess really quick, the same thing would happen if I had like A times B times C times D. So if I had 4 things being multiplied together, a couple of ways you could do that is you could group all of them like this, A, B, and C together, and d by itself. But then when you take the derivative of this, you're going to have to do the same thing. You have to break up to put two of them together and take that. This is going to be like 3 product rules in one, right? The other way you could do it is still going to take 3 product rules, but you could group them like this. So there's your first one. That's your u, which is going to require another product rule. Here's your v, which when you take the derivative of that is going to require another product rule, and it gets really messy. So you can see why product rules are so much fun. One other thing I will say about the product rule, though, because of the way addition works, it doesn't matter. Like if you learn the rule to be v prime times u plus u prime times v, that's the exact same thing. It's just taking this term right here and just moving it to just swapping terms with this one. And that's totally fine with addition. It doesn't matter. 2 plus 3 is the same thing as 3 plus 2. However, in just a second, we're going to see on the quotient rule, that is not the case. We have to do the quotient rule in a very specific manner. All right, here we go. The quotient rule. As you can see, it is kind of a mess. There's a lot going on here. And once again, it's not as simple as the sum difference rule where you just take the derivative of the top and the derivative of the bottom and call it good. There's a lot more to it. So let's just kind of walk through this first one. We need to identify what our u value and our v value are. So u in this case is going to be sine of 2x. That's my u. And v is going to be cosine of 2x. All right, here we go. Buckle up. All right, the derivative for y is dy over dx. And the quotient rule says, in the numerator, we're going to take the derivative of our numerator. So the derivative of sine of 2x, that's a sine rule. So that's going to be sine of 2x times the derivative of the argument, right? So that's the chain rule part of that. Which is 2. I'm going to put the 2 out in front. Once again, I'm going to put these in parentheses so I can see I'm getting all of my stuff. So I've got that one. There's that my u prime, right? Next one is v, written just the way it is. So cosine of 2x, just the way it is. Minus the derivative of our v. Derivative of cosine is negative sine of 2x times the derivative of 2x, right, the chain rule, which is 2. Notice how I just left the negative sign out here. If you want to kind of think through that and already make that positive, you're welcome to. I like just leaving the negative sign there so I don't accidentally forget to do that, but do what you want. Our u value is sine of 2x, written just as it is, no derivative. All divided by, so the whole thing is being divided by our denominator, cosine of 2x, squared. So cosine of 2x left just the way it is, I'm not taking the derivative or anything, squared. And that right there is the derivative of sine of 2x over cosine of 2x. So I do want to clean this one up a little bit because I want to show you something. I picked this one for a reason. So let's clean this up. We got dy over dx is equal to, what do we got here? 2, positive 2 sine of 2x cosine of 2x. So 2 sine of 2x cosine of 2x. Okay. This becomes plus 2 something. Yeah, that's right. Something's wrong here. Is this right? Derivative. I didn't take the derivative of sine. Oh my goodness. I'm like, this should not be 2 sines x's. I am so sorry. Totally messed that up. Let's kind of cut back a little bit here. We got to fix something. It's a good thing I'm going back through and simplifying this. That should not have been sine. That should have been cosine right there. People are probably watching this screaming at me. Hey, you did that wrong, you fool. Okay. Sorry, we all make mistakes. All right, so this should be, sorry, when I was taking the derivative of sine of 2x, the derivative of sine is cosine. I accidentally just wrote sine. So this is cosine of 2x. There we go. Cosine 2x, cosine 2. That looks better. I was like a little nervous that my little trick that I was going to show you, not trick, but the reason why I chose this one, like it's not going to work. What's going on? All right, so we've got 2 cosine 2x times cosine 2x. So I can call that cosine squared of 2x. I can multiply them together because their arguments are the same. Over here I can do the same thing. I've got plus 2 sine of 2x times sine of 2x. So that's sine squared of 2x. Just so you know, this was the derivative up here. I'm just simplifying it. So I'm done with the calculus aspect to this. I'm just simplifying this for a special reason. And then I've got cosine squared, right? I can just make this, instead of writing it like this, I can write it as cosine squared of, of Control Z, of 2x. Okay. Now, if you remember your trig identities, I can factor out a 2 out of this. I'm left with cosine squared of 2x plus sine squared of 2x, right? All over cosine squared of 2x. Let me move this little guy down here down a little bit. He's in the way. Yeah, let's bring him down about right there, like so. All right, your trig identities, I've got sine squared plus cosine squared. Doesn't matter what the argument is, but sine squared plus cosine squared is always equal to 1. So this up here, this is actually 2 times 1. Let's put a little cosine. 2 over the cosine squared of 2x, which you could leave it like that, but 1 over the cosine is secant. All right, yeah, it's secant. 1 over the cosine is secant. So 1 over cosine squared is secant squared. So this is the exact same thing as 2 times the secant squared of 2x. And that's how that really long, ugly derivative would simplify. Now, the reason why I chose that is, once again, if you do remember your trig identities, sine divided by cosine, they have the same argument. Sine divided by cosine is just tangent. This is tangent of 2x is what this equation is, really. They mean the exact same thing. So instead of doing the quotient rule, I could have just said, hey, what's the derivative of tangent of 2x? We come down here, tangent derivative is secant squared of 2x times the derivative of 2x, which is 2. So I chose this one for a reason, to show you that, yes, the quotient rule is necessary. In order to have gotten this answer, I had to have done the quotient rule. I couldn't have simply done the derivative of the numerator divided by the derivative of the denominator. All right, let's take a look at this guy right here. So we've got f of x is equal to e to the x over 5x. This one I just chose for fun. There's nothing special about this one. So we've got f prime of x is equal to derivative of the top, which is e to the x. The top is e to the x, and its derivative is also e to the x, times the bottom, just the way it is, minus the derivative of the bottom, which derivative of 5x is 5, times the top, just the way it is, and finally divided by the derivative of the bottom, well, not derivative, sorry, just the bottom, 5x squared. And there is our derivative right there. That you could clean that up a little bit. I'm not going to, because I'm lazy, and that is the answer. That is the derivative, and you're done. So that ends up with the quotient rule. One other thing I want to mention with the quotient rule, because it's, it might seem hard to memorize. I've seen some books that write the product rule in a different order. They write it as v prime first and then the u prime second. So they've got these switched around. I like writing the product rule like this because you'll notice that it is, if it's written like this, it is the exact same thing as the quotient rule, just with a minus sign instead of a plus sign. Right, and then you have the v squared on the bottom. There's also a little rhyme you can memorize if you want for the quotient rule. So the quotient rule is low d high minus high d low square the bottom, and away you go. So let me explain that. So you have the low. So you put the low thing first. So low is v. That's the denominator, right? So this is low times the derivative of the high, so u prime, minus the high. I don't know why I just put h, but that's okay. I meant high. High, which is u. D low, so that's the derivative of the denominator. And then square the bottom. So that's v squared, and that goes on the bottom, and away you go. So you'll notice this that I have written up here in blue and green is the exact same thing as this. It's just that the multiplication problem is turned around. So these are switched around, which is just fine, right? 2 times 3 is the same thing as 3 times 2. So that's nice to remember. Low d high minus high d low, square the bottom, and away you go. You can memorize that if you really want to. So anyways, that does it. That is the quotient rule, and that finishes up all of these derivative rules that we have over here on the right. Hopefully that was a worthwhile video. Even if you just watched part of it, that's great. Hopefully it was helpful, and good luck with calculus. Calculus is awesome. There's a lot of cool stuff with calculus.